I am so excited, and I just can't hide it. Wow, it's my first date. I can't wait. I am so excited, and I just can't hide it. Oh my God, I can't wait to see. I can't wait to see her. And I just can't hide it. I'm so excited, and I just can't hide it. Hey, let me pull in here. I ran out of gas. Ish, I don't have cash to pay. Let me use a card. Damn, what just happened? Power failure? Damn, what should I do now? I don't have cash. I can't take my car, and my dad is waiting for me. I'm stuck. I guess I should wait. I don't have a choice. Yippee! The power is back. Now I can finally pay for my gas. What? What do you mean the payment couldn't go through? The money was withdrawn from my card. Oh damn. I shouldn't be here. How could this happen? It's my first day. And she'll think I stood her up. And now I may never get another chance.
Hi, my name is Bart. Bart as in B-A-R-T. Well, the scenario that you just seen happens to one of my good friends, Mickey Mouse. Well, that just shows that some transaction systems are not reliable. For a system to be reliable, well, the transaction system to be reliable, it must go through under acid tests. That is why our topic today is about putting the database into acid test reliably. Now, please don't fall asleep during my lecture because I'll tend to use what I'm holding on my back. You see what I'm holding on my back, right? Well, now taking a look at the word ACID. ACID is actually an abbreviation for atomicity, consistency, isolation, durability, and serializability, which are all properties that guarantees database transaction are processed reliably. Oh, what do we have here? Well, atomicity. Atomicity is a property that guarantees that an incomplete transaction cannot exist. Database modification must follow an all or nothing rule. By an all or nothing rule, we mean that if one part of the transaction fails, the entire transaction fails, and the database left unchanged. Now, looking at the property consistency. This actually ensures that any transaction will take it from one consistent state to another. Well, by that we mean that only valid data will be written on the database. If for some reason a transaction is executed that violates the database consistency rules, the entire transaction will be rolled back and the database will be restored to the consistent state with those rules. Wow. Well, taking a look at the property isolation. Isolation ensures that a transaction should not be able to interfere with another transaction at all. It should not be possible that two transactions affect the same rules run concurrently. Well, for an example, let's say John issues a transaction at the same time that Melissa's issues a different transaction. Both operations should operate on this database in an isolated manner. The database should either perform John's entire transaction before executing Melissa's or vice versa. Oh boy, we are still not done with the acids. Well, the D part on the acids test is durability. Well, here, every committed transaction is protected against power loss, crash, errors, and cannot be lost by the system and thus guaranteed to be complete. Well, I know that you're waiting for the S part of the acids test. Well, the S part on the acids test is the serializability. Well, this is the highest isolation level. It specifies that all transactions occur in a completely isolated fashion, or in other words, as if all transactions in the system had executed serially, meaning one after the other. Well, cool. Well, for further explanation of these properties, we are going to use examples. Say the database has two fields, A and B, in two records. And integrity constraints requires that the value in A and the value in B must sum up to 100. As you can see, the code, the SQL code on the board, which shows what I just described. Well, from that example, now I'll walk you through atomicity failure. Say the transaction subtract 10 from A and adds 10 to B. If it succeeds, it will be valid because the data continues to satisfy the constraint. However, assume that after removing 10 from A, the transaction is unable to modify B. If the database retains A's new value, atomicity and the constraints will both be violated. Atomicity requires that both parts of this transaction are complete or neither. Well, now let me kick back and relax and tell you more about consistency failure. All validation rows must be checked to ensure consistency. Assume that a transaction attempts to subtract 10 from A without altering B. Because consistency is checked after each transaction, it is known that A plus B equals to 100 before the transaction begins. If the transaction removes 10 from A successfully, atomicity will be achieved. However, a validation check will show that A plus B equals to 90. That is not consistency according to the rules of the database. The entire transaction must be cancelled and the affected rows rolled back to their pre-transaction states. Hey! Now the isolation failure. To demonstrate isolation, we assume two transactions execute at the same time for each attempting to modify the same data. One of the two wait until the other completes in order of isolation. Consider two transactions. T1 transfer 10 from A to B. T2 transfer 10 from B to A. Combined the four actions. Subtract 10 from A, which is another action. Add 10 to B, another action. Subtract 10 from B and add 10 to A. If the operations are performed in order, isolation is maintained, although T2 must wait. Consider what happens if T1 fails halfway through. The database eliminates C1 effects and T2 sees the valid data only. Wow, how cool is that? Hey! Now the isolation failure. To demonstrate isolation, finally, durability failure. Assume that a transaction transferred 10 from A to B. It removes 10 from A, it then adds 10 to B. At this point, a success message is sent to the user. However, the changes are still queued in the disk buffer, waiting to commit the disk. Power fails and the changes are lost. The user assumes that the changes have been made. Well, that's pretty much it about the SS test.